Welcome to Physics and Reality with Prof. Stuckey. I'm Emeritus Professor of Physics, Dr. Mark Stuckey, and in this video I'm going to explain why Tim Maudlin has some mistaken claims about implications for the violation of Bell's inequality. In order to keep this video relatively short, I'm going to omit some details. If you want to see those missing details, you can read our 2024 book with Oxford University Press, Einstein's Entanglement, or read our published papers linked in the video description. When Tim talks about quantum entanglement and the violation of Bell's inequality, most of what he says is spot on. He's far more knowledgeable than most in quantum foundations. He really gets it. For example, in his paper, What Bell Did, he writes, "The experimental verification of violations of Bell's inequality is the most astonishing result in the history of physics." But his decades of research on this astonishing result have led him to some radical conclusions. In his book, Quantum Non-Locality and Relativity, he writes, "One way or another, God has played us a nasty trick. The voice of nature has always been faint, but in this case it speaks in riddles and mumbles as well. Quantum theory and relativity seem not to directly contradict one another, but neither can they be easily reconciled. Something has to give. Either relativity or some foundational element of our world picture must be modified. The real challenge falls to the theologians of physics, who must justify the ways of a deity who is, if not evil, at least extremely mischievous." In this video, I will explain why the violation of Bell's inequality is not evidence for an evil or extremely mischievous deity, but quite the opposite. His second mistaken conclusion is that the violation of Bell's inequality means special relativity is incompatible with quantum mechanics and is in fact wrong. Here are some slides from a recent talk in Italy titled "The Great Rift in Physics: Tension Between Relativity and Quantum Theory." The problem here is worse. There appears to be a much more direct conflict, a straight contradiction between relativity and quantum theory. On the one hand, relativity is understood to imply that nothing goes faster than light. On the other hand, the usual understanding of John Bell's famous theorem is that certain observed correlation between experiments done far away from each other cannot be predicted or explained if no causes go faster than light. Bell's inequality. This is what Einstein called spukhafte Fernwirkungen, or spooky actions at a distance. He concludes, basically what Bell proved is that relativity can't be right. In this video, I will show just the opposite. Special relativity and quantum mechanics are not only not in conflict, they are both what Einstein called principal theories, and further, they are based on the exact same principle. There is nothing wrong with either theory. All the physics is spot on. Here you see what Bell wrote to open his famous paper. The paradox of Einstein, Podolsky, and Rosen was advanced as an argument that quantum mechanics could not be a complete theory, but should be supplemented by additional variables. These additional variables were to restore to the theory causality and locality. And note, Maudlin, Bell, and I are all choosing to ignore the violation of statistical independence. That's one of the details I'm omitting in this video. That's the point Maudlin is making in this slide. Causation can't go faster than light, and events at space-like separation cannot be causally related to each other. They could, of course, both be effects of some common cause. Brundis makes that point in this paper. Bell's principle of local causality, in either of its equivalent forms, 10 or 11, there on the left, implicitly depends on an assumption that goes beyond questions of locality. That implicit assumption is called Reichenbach's principle of common causes. That is, Bell is assuming causality and locality when he derives his inequality, and Tim is following suit when he says in his previous slide that the violation of Bell's inequality, quote, "cannot be predicted or explained if no causes go faster than light." Einstein was faced with a similar situation in the late 1800s when physicists were trying to find a causal mechanism to explain why everyone measured the same value for the speed of light c regardless of their motion relative to the source. That is, they sought a causal mechanism producing length contraction leading to the observer independence of c, whence the Lorentz transformations. But after years of failed attempts, Einstein writes, "By and by I despaired of the possibility of discovering the true laws by means of constructive efforts based on known facts. The longer and the more despairingly I tried, the more I came to the conviction that only the discovery of a universal formal principle could lead us to assured results. That is, he abandoned a causal explanation for the light postulate, constructive efforts, and instead said it had to be true, as pointed out by John Norton in his course on special relativity. The principle of relativity assured Einstein that the laws of nature were the same for all inertial observers. That light always propagated at the same speed was a law within Maxwell's theory. If it held in one inertial reference frame, it had to hold in all of them. So, if the principle of relativity was applied to Maxwell's law about light, the light postulate resulted immediately. Thus we see that special relativity is what Einstein called a principle theory, which means its kinematics follows from an experimentally discovered fact, the observer independence of the speed of light c. And that fact must be true if the relativity principle and Maxwell's equations are true. In this respect, special relativity produced a principle explanation. This is so widely accepted that it appears in introductory physics textbooks without qualification or controversy. Today, we still have no consensus causal/constructive counterpart to special relativity, and physicists long ago gave up looking for one. My colleagues and I call the relativity principle no preferred reference frame, or NPRF for short. So we have Einstein's principal solution to the mystery of length contraction as follows. The relativity principle and Maxwell's equations demand the observer independence of c, whence the Lorentz transformations containing length contraction. Notice that in this view, length contraction is not a dynamical effect resulting from some causal mechanism like the luminiferous ether. Length contraction is a kinematic fact that follows from the observer independence of c, which follows from the relativity principle and Maxwell's equations. Okay, whose meter sticks are shorter? Consider the following three events, labeled with the x and t space and time coordinates of two different reference frames in motion relative to each other. Times are exaggerated for effect. In one reference frame, you have three sisters all the same age, and Alice is one of them. In the other reference frame, you have two brothers, both the same age. Bob is one of them. The sisters and the brothers agree on the data labeling these three events as related by the Lorentz transformations, with exaggerated time differences. Since the brothers are the same age, events 1 and 2 are simultaneous for them, and it's obvious from their organization of the events that the sisters' meter sticks are short, since sisters measure the distance between Sarah and Alice to be 1250 kilometers, while the brothers measure it to be just 1000 kilometers. But the sisters are all the same age. So they say event 2 happened 2.5 years before event 1. The event that happened at the same time as event 1 is event 3. So from their perspective, it's the brothers' meter sticks that are short, since the brothers measure the distance between them to be 1000 kilometers, while the sisters measure it to be just 800 kilometers. What causal mechanism is shortening meter sticks per this relativity of simultaneity? None. Length contraction is not a dynamical effect. It's a kinematic fact that follows necessarily from the observer independence of c as required by the relativity principle and Maxwell's equations. Just like Maudlin did in The Great Rift in Physics, let me use electron spin to depict our entangled property. As Stern and Gerlach sent silver atoms through a non-uniform magnetic field, they found the atoms were deflected up towards the north magnetic pole, or down towards the south magnetic pole, never anywhere in between. The deflection was eventually attributed to the spin angular momentum of the silver atom's valence electron, which equals plus or minus Planck's constant h from his black-body radiation law, divided by 4 pi. So, as Steven Weinberg pointed out, when you measure electron spin with Stern-Gerlach magnets, you are measuring Planck's constant h. What's true about such measurements is that the electrons are always deflected the same amount up or down relative to the north-south magnetic poles for a particular source, no matter which way the Stern-Gerlach magnets are aligned in space. We can restate that as an experimentally motivated postulate, like the light postulate. Everyone measures the same value for Planck's constant h, regardless of how they are oriented in space. Now let me show you how Einstein's principal approach allows us to explain quantum entanglement and the violation of Bell's inequality without spooky actions at a distance. Suppose you first measure an electron vertically, or in the z-hat direction, and find its spin is up. Then you measure its spin in some direction b hat, making an angle theta with z hat as shown here. What do you expect to find? Well, since spin is a form of angular momentum, Newtonian mechanics says you will simply obtain the projection of plus 1 z hat in the b hat direction, or plus 1 cosine theta. But since we're measuring Planck's constant h when we do a Stern-Gerlach spin measurement, we can't obtain a fraction of h, or a fraction of plus 1 here. However, plus 1 and minus 1 outcomes can average to cosine theta, and that, with the requirement that all probabilities must total to 100%, gives us the spin 1/2 probabilities of quantum mechanics. Thus, the relativity principle and Planck's radiation law tell us that quantum superposition resides in this average-only projection. So how does this lead to quantum entanglement and the violation of Bell's inequality? To remind you, Alice is measuring her spin-entangled particle in the a hat direction, Bob is measuring his in the b hat direction, and the angle between a hat and b hat is theta. When Alice and Bob make their measurements in the same direction, a hat equals b hat in our previous picture, they always obtain the same result as necessary to conserve spin angular momentum. Half the time both are plus 1 and half the time both are minus 1. So in those trials when Bob happens to measure in a different direction, b hat doesn't equal a hat, Alice reasons exactly as the same as the single particle case. That is, the spin angular momentum of Bob's particle is the same plus or minus 1 a hat as her particle. So when he measures that plus or minus 1 a hat angular momentum in his b hat direction, he should get plus or minus cosine theta. But just as with the single particle case, Bob cannot obtain a fractional value for a measurement of h. However, his result can average the required plus or minus cosine theta. Thus we have this average-only conservation of spin angular momentum for the spin-entangled pair of particles, just like we had average-only projection of spin angular momentum for the single particle case. Of course, since there is no preferred reference frame, Bob can make the exact same claim about Alice's result relative to his measurement direction. And when you demand that all the probabilities add to 100%, you get exactly the joint probabilities of quantum mechanics that violate Bell's inequality. So, contrary to Maudlin's claim, Einstein's principal approach allows us to derive the joint probabilities without invoking spooky actions at a distance. That is, the Bell inequality violating correlations can be predicted and explained without causes that go faster than light. Who needs to average their data? Consider the following data obtained by Alice and Bob when making spin measurements on a pair of spin-entangled particles with theta equals 60 degrees. Alice and Bob agree that these data are correct. When Alice organizes the data per her plus and minus 1 results, it shows clearly that Bob's data averages to plus or minus cosine theta, or 1/2, according to average-only conservation from her perspective. Here, if you see Bob's data corresponding to Alice's plus 1 outcomes, he got plus 1, minus 1, plus 1, plus 1, which averaged to 1/2. But when Bob organizes the data per his plus and minus 1 results by switching rows 2 and 6, it shows clearly that it's Alice's data that averages plus or minus 1/2 according to average-only conservation from his perspective. So what non-local causal mechanism is responsible for this average-only conservation? None. Quantum entanglement is not a dynamical effect. It's a kinematic fact that follows necessarily from the observer independence of h as required by the relativity principle and Planck's radiation law. So, Maudlin's constructive efforts lead him to conclude, I like to think if Einstein had lived another few years and saw Bell's result, he would have appreciated it and said, well, I didn't like action at a distance, but I'm stuck with it. That is, Maudlin believes Reichenbach's common cause principle is fundamental. So, the violation of Bell's inequality due to quantum entanglement is evidence that special relativity is wrong and in conflict with quantum mechanics because there is a preferred perspective on reality due to a deity that is evil or extremely mischievous, giving us a physics that is hideously incoherent. Alternatively, you can choose to believe Einstein's relativity principle is fundamental, in which case the violation of Bell's inequality due to quantum entanglement is evidence that there is no preferred reference frame, so the relativity principle grounds both special relativity and quantum mechanics because the deity is benevolent per strict impartiality, giving us a physics that is beautifully coherent. Given what you've learned in this video, how would you place your bet?